Hello and welcome back to Calculus 1 Saturday edition, talking about 5.5 U substitution, known as Usub, which is one of the most used integration techniques in all of calculus. And the reason why it is one of the most used techniques is because it's backwards chain rule. Now, this is more of a procedure than a formula, even though formula could be written, but it's completely useless. It's one of those cases where, it's awkward, right? Where I say, okay, we have a formula, but it's useless. So, what is the deal here? Well, the way this works is you identify the part that bothers you, the part that makes the problem not be the basic problem. And then you replace that with a single variable u. It doesn't have to be u, could be w, could be g, could be whatever, but we usually use u. And it makes it funny, you'll see why. So if I have something like this, 4x plus 3 raised to the 17th power dx, right? You go and you say, oh, I gotta FOIL this 17 times. This is actually 16 times. This is insane. I'm not gonna sit here foiling this for the rest of the day. And yeah, you're right. You shouldn't be, right? You shouldn't be sitting here foiling this for the rest of the day, because we can also go into this kind of back of the mind thing, which I usually say, I know that I can easily do this integral, right? So this is one of the methods that helps me to say, well, can I just replace this mess with a single variable, which would make this just u to 17 and make it beautiful. But then there is this problem of dx. That needs to be changed as well. You can't go and change x dimension into a u dimension and keep dx. That makes no sense. So if I'm switching to u dimension, I better have du as well. So I need to figure out what du is, and that we can easily figure out by differentiating here and then just move dx to the other side. Now remember, I'm replacing dx. So solve for dx so you can just plug it in and you get du over 4. So du over 4 goes in here, and that creates the integral 1/4 integral of u to 17 du. And now you transformed your mess of the integral up there into a basic 4.9 integral on the bottom. Now we know how to solve this integral, which is u to 18 over 18 plus c, which is 72. So 1 over 72 u to 18 plus c. Now we're not done, because no one cares about u. I mean u variable, not u. We want x values back into the story, so you substitute back, and then you are done. So now we have the solution. So when you are looking at this problem, we replaced this mess 4x plus 3 with one variable and then went through the procedure to deal with this. Now, that is possible for problems that are, just messy, but you can deal with this. Let's take a look at another problem that looks messy, and this is the one that will be very frequent in your let's say partial fraction decomposition Calc 2 section, where you're going to see this so much that the entire process now that I'm going to do, you will just instantly know. You will not write any of the stuff. You will just write the solution for it. That's how much it's gonna be used. For instance, integral of 4 over x minus 3 dx, like integral like this. Now, there is always that no part that lights up in your brain, hopefully, right, if you populate it with 4.9. And that no part is, 1 over x dx is ln of absolute x plus c. Right? So your brain is populated with this from 4.9, and you are recognizing that form here, except it's not exactly that, but it's kind of close if you kick 4 outside, which you can. And then you do something with this x minus 3, which is obviously u equals x minus 3 to make it into a single variable, which is what you need. In which case du dx is just 1, from where du is the same as dx. This problem transforms into 1 over u du, and that is your ln. So this entire process, no integral now. This entire process is going to be automated in your head when you jump into, let's say, integration by partial fraction decomposition in Calc 2, which is again one of the basic skills for differential equations later on to do inverse Laplace. So we can jump, through calculus courses of where this is going to be used. And you are not going to see Calculus 2 students write any of this. Once you're in Calc 2, you go directly from here there, like instant jump, because the top number goes in front and x minus 3 goes in absolute values. And if I am to jump into Calc 2 lecture, you would actually see it there without any of the work in between, because those integrals will be so frequent, right? You will just make that jump right away. You literally do like 50 of these, more. So these two problems had something similar in mind. They were very close to a very basic 4.9 problem, and they both were solved by replacing the mess that is bothering you with a single variable, and you're done. Now, somewhat more advanced situation is when you have something like this. Now, I can't really use the I know from before. I mean, I could, but it doesn't really, it does help, but there is a much better way to talk about it. You can say, I know that the integral of cosine x dx is sine x plus c. Again, you're flexing with your 4.9 knowledge. And then because I know cosine x, but I have x squared, You could make the argument of u equals x squared, du equals 2x dx, right? And go from there. There is a better way, which I'm going to present also. Now, when you have this approach, right, I know that if I just had the, right, it doesn't really address this x at all. It addresses only this part, and you literally stumble upon the solution if you ask yourself the right question, which is why I usually do not approach this way. But this way is exactly the same approach as the previous two problems. And there is no other way of solving this other than saying u equals x squared. I mean, that's not going to change. It's just the way you think about it to get there changes. I will talk about that as well. Okay, so now I'm ready to make my substitutions. And I see this part here, but over here I am missing a 2, as you can see, right? Because it's 2x dx. And for constants, you can fix that. You can literally just put 2 and 1/2 in front to balance it out, and you just fixed your problem. So now when you do your substitution, you're going to have 2x dx is just du, and you have cosine of u in there. So now you will have 1/2 sine u plus c, and right, you have to go back to x variable. So 1/2 sine x squared plus c would be the answer, right? So that's we're done right there. That's too dramatic. Less dramatic. There we go. So for this problem, we said, okay, I know how to deal with the cosine of x. I don't know how to deal with cosine x squared. I do know how to deal with cosine x. Okay, so what's bothering me? X squared is bothering me. So let me replace that x squared with a single variable so that I can make cosine of x. In this case, cosine u, when we do the substitution. So it is a valid approach. But as I said, it doesn't at all address that x in front in your thinking. And you literally stumble upon the solution without even considering that x as a part of your problem at all. And that's an issue. That's an issue when you can kind of solve the problem without considering all of the problem in your thinking, because you're not going to have too many of those cases down the line, right? This could be, oh, this is a very nice, simple, straightforward case, thank you, pretty much, right? But what is the better way to approach this, solve the same problem of x cosine squared x with the same substitution? Not cosine squared, cosine x squared. There we go. Solve the same problem with the approach. Well, this is the new thing now. You are looking for function derivative pair. You are trying to locate two separate functions that are not in composition or anything. They're not involved with each other than through multiplication or division or whatever. So you're trying to find two functions that have this relationship of function derivative. And clearly for this problem, that's going to be x squared and x, which is 2x actually is the derivative for this problem. And your u will always be the function. This is way more powerful way to approach U sub than I know approach. Because I know approach never considered x. It only considered O, right? What we're going to do with x squared, which will create problems for you if you only know this approach. Then in Calc 2, you will not be able to differentiate very well between the integration by parts and U sub, and so it creates a lot of problems there. So I like to kind of, force this kind of approach where if you have function and its derivative present, most likely it's U sub. If you don't have it, then it could be something from Calc 2. Now, unfortunately, not too many of us teach it this way because it's so much easier to say to students, well, if it's not a basic integral, obviously it's the U sub. Yeah, you have only two techniques. It's either a basic integral out of the box, integral of sine, integral of 1 over x, integral of x to the 7, right? The basic thing from 4-9. Or if it's more complicated, it's a U sub. But what you're going to do when you go into Calc 2 and you add another 5 differentiation techniques, right? And you never learned function derivative pairing. Because function derivative pair is the one that kind of spells out you're supposed to use U sub because that's what you have in your chain rule, which I'm going to show off later. The solution of the problem is absolutely the same. I mean, I have nothing new to write. It was actually function derivative pair why I did this. So now when I do the substitution, I'm still going to fudge the 2 and the 1/2 over here, have 1/2 integral of cosine u du, and I'm just going to say same. I'm not going to waste time. Now, I do want to contrast this problem with this problem. And see, the I know approach is going to be very, very difficult to deal with in this case. Because you can say, oh, I know that the integral of cosine is sine and integral of sine is negative cosine. But it doesn't really paint the picture because those are two separate I knows, but both of them are appearing in a problem. So even though it can be used, it's much more powerful if you say what's the function derivative pair. And we can just do FD, function derivative. So the derivative of cosine is negative sine, and derivative of sine is cosine. Now, a lot of people would say, well, I don't want to kind of use the negative sign, so let me try with u equals sine x. So because these are like two options you have, right? So let me use the bottom option. But if you use the bottom option, which is not correct choice, you would see that you can't solve the problem. So let's try it. And this is very important, guys. It's very important to fail many times on your substitutions, obviously, while practicing and learning. If you only do 5 homework exercises for this section, I mean, you are doomed with like 7 O's, not 2 O's, but 7 O's in the spelling of the word doom. Actually, doom, right? There we go, 7 O's. There is no formula here. It is all experience just by doing thousands of problems. And I want to fail on this one just to show you what happens when the problem fails, when substitution fails. Because we all want to use this one. It will be du over dx and you move dx on the other side. Because this one, it has no minus sign, so it's like, yeah, this one is cool, right? Let's use this. But look how quickly hell breaks loose when you try to substitute this. You would go and you would say, okay, integral, and now I have one of the cosines So 9 will stay, and one of the cosines will go into a du, and I have a u. And what the hell I'm going to do with this? Because I did the replacement, right? So as you can see, sine x went into this, and then one of the cosines and a dx went into du, looking at the substitution. So I still have 9 cosines hanging around. Not everything was substituted. So, half of my problem is now in the u dimension, and half of the problem is in the x dimension. And that's no bueno. So when the substitution goes wrong, you either get worse problem than you started off, or impossible problem, which is this one. Because I can't integrate because I still have x hanging around. So we have to abandon this, and I'm going to abandon it this way, and say, okay, u equals cosine x, and the du is equal to negative sine x dx. Aha! All I need to do is to make this negative, right? You put 2 negatives. So now your cosine x is u, so this becomes u to the 10, and then I have a negative sine x dx to become du. Ooh, all of a sudden it worked. When you make a right substitution, the problem collapses into something basic from 4.9, and you are able to integrate instantly. So, negative u to 11 over 11 plus c, and then you go with no one cares about u, care about the x, which means you bring back your cosine to the 11, x over 11 plus c. So that's the way to solve the problem. You are going to make a lot of wrong substitutions because you are not experienced, and that's just the fact. Literally anything from plumber to nuclear physicist, everyone learns the same way. Mess it up many times, and then finally, when it starts clicking, you start getting it right. No one will ever convince me that anyone's first tiling job went perfectly, because it's not going to happen. It's going to be a failed, terrible job, but it was a learning experience, and it's a heck of a better than a 0, infinitely better than 0. So the only way to be worse than being wrong is not to do it at all, right? That's the thing. You look at it and you say, oh, I don't know, and just walk away. That's worse than getting it wrong. Because when you get it wrong, you at least learn what is wrong, and then maybe you get it another 5 times wrong, but then you eventually get it, right? That's the process of growth and learning. So the only invalid question over here is, how do you know? Well, I invested hours in practicing to know. And this problem is kind of designed for you to see that both of these are valid ideas to start from, but only one of those two works. And you can pretty much see that when you do the substitution. Which is why, right, if you take an hour, and a half to do the test, I can do it in 20 minutes. Because I'm not going to explore. I already know what am I supposed to use, and I just use it and I'm done. Where on the test, you are going to start the problem wrong, then you're going to see that it's wrong, you're going to get stuck, you're going to abandon it, you're going to try the other approach, that's going to work, you still need to calculate, right? That's why you are not getting 20 minutes for the test, right? Because if I can do it in 20 minutes, that means it can be done in 20 minutes. But again, I don't have to go through the hoops of, oh, this didn't work, or, you know. So these are the things that you will get with experience, and which is why I'm saying do not play with fire to just do 5 exercises because that's the bare minimum we can pass the homework grade with, right? Do 30. Do yourself a favor and make your Calculus 2 class possible. Because if you don't know this, you're done. There is no Calc 2 for you. Because most of the problems, integrals in Calc 2 are integration by parts. Oh, sorry, Usub. Right, Usub, and the rest is integration by parts. That's a story for Calc 2. We don't have to talk about it here. All right, let's take a look at another one. Always function derivative pair. That's what we're looking for. Function derivative pair. So I have integral of 2x plus 1 divided by the cube root of x squared plus x minus 7 dx. It looks terrible, right? So what are you going to do if you say, oh, I know that the integral of 2x plus 1 is, or whatever, or what I know what the integral of cube root is, or I know what the integral of x squared. Like, it's hard to approach the problem from that perspective when you have these many functions floating around. Granted that this is a function composition, right, which is where you should be digging, but we're not there yet. So what's my function derivative pair? Well, you guys have 3 functions to worry about. There is a 2x plus 1 function, there is a cube root of x function, and there is x squared plus x minus 7 function. So which of the 3 functions has its derivative present? It's not a trick question, by the way.
X squared plus x minus 7.
Is a what? Function or the derivative?
That's the derivative. Or no, that's the function, and the derivative is 2x plus 1.
Excellent. Yes. So you actually cracked the problem. And as soon as you realize that, you're technically done. Because x squared plus x minus 7, whose derivative is 2x plus 1, solves the problem. Integral of cube root of u, because we said that u will be x squared plus x minus 7, and the du will be 2x plus 1 dx. Look how beautiful that works. You see that in this peanut over here, you have 2x plus 1 times dx, which is exactly what you have over here. So that's going to be your du. So what's left on top? Just 1. And we converted this to a basic 4/9 integral in one shot. In one shot, we cleared out all of the mess. And what we have now is integral of u to the negative 1/3 du. That's solved with the x to the n thing, right? So you see how much it simplifies when you have the right substitutions. And now all we need to do is say u negative 1/3 plus 1, right? Negative 1/3 plus 1 plus c, which is u to the 2/3 divided by 2/3 plus c. And we have 3/2 u to the 2/3 plus c, which gives 3/2 of x squared plus x minus 7 to the 2/3 plus c. And that's the solution. So now you can hopefully see the entire problem. And again, if you make any other choice of u, you are going to get stuck. If you choose u to be 2x plus 1, the derivative of that is 2. You don't get to address anything in denominator, right? All of the x's stay around, and obviously problem is gone. If you choose to have a cube root as u, then there will be another cube root in the derivative, and you don't have another one. So there is a lot of problems and issues and things that arise when you are trying to solve this. So you might be skeptical. You might say, well, is this really an answer? And the answer to that is check it, right? The reason why, as a student, I loved integration more than derivatives is because I could check, right? For derivatives, you don't have a check procedure. You can redo the problem, and if you make the same mistakes, right, or you lack knowledge in whatever, you're going to get it wrong every time. But for integrals, all you need to do is to differentiate your answer, right? If you're not lazy, right? That has to be said. If you're not lazy, you differentiate your answer, and if you get your starting problem, you know it's good, which is what I used to do, because it was, right, it was like, oh, okay, integration. My grade for integration was 100 throughout. Every exam, every quiz, every single thing about integration for me was 100, because I had the discipline of taking derivative of the answer and making sure that it matches 100% the problem I started from. And when it doesn't, I know something is wrong and I have to look into it. So the check procedure over here is a joke, right? All you need to do is obviously the chain rule. So if you want to check this, you're just going to take the derivative of 3/2 x squared plus x minus 7 raised to the 2/3 plus c, right? Now, derivative of plus c is 0. You don't even have to write it, right? Because derivative will always kill it. So copy your constant, drop down 2/3 x squared plus x minus 7 to the negative 1/3 because you're subtracting 1, right? It's a derivative. And then times the derivative of the inside, which is 2x plus 1. These guys cancel, and then you have your 2x plus 1 divided by the cube root of x squared plus x minus 7, which is exactly what we have, right, as our integral here. It is absolutely easy to check. It just, as I said, laziness gets in the way. Or the other one, which is much worse, I don't care. I just did my problem and I don't care. I don't know. No, yeah, definitely. Apathy is worse than lazy, because when you're lazy, you still kind of care about it, because it keeps bothering you. You think you're just lazy to do it. But when you don't care, it's kind of vacate. I think it's worse when you don't care than when you're lazy. I don't know. That's a philosophical discussion that we could have next week. Which one is worse? We need to first finish the course. So you have this option to check in every single one of your integral problems, right? You have the option to take the derivative and get the answer at the end. All right, let's take a look at another problem. Oh, you know what is cool? I almost forgot. E to the 4x dx. I asked you to memorize the formula for e to the ax in 4.9 because, right, it's just one of the formulas. But here is the way it's actually done, right? And this is actually one of those I know problems because you're not going to look for function derivative pair here, right? This is I know that integral of e to the x dx is e to the x plus c. So I know that I'm supposed to put 4x, right? And then du is equal to 4 dx. And then dx is du over 4. Or you can fix it if you want to. Whatever is your favorite, guys, you can actually stop here and then just fix it with a 4 and 1 over 4. You can do that. Or you can use this line on the bottom and say, okay, this is e to the u and then du over 4. Right? You're going to end up with over 4 either way. Like, I really don't care which way you do it. Just get it right. So this is going to be 1/4, right? It still ends up being the same problem. And that's 1/4 e to the u plus c. And then, right, no one cares about u, care about the x, which means e to the 4x plus c. Now, if you go back into 4.9 lecture, I wrote somewhere that e to the ax dx is equal to e to the ax over a plus c. There's your over a, right? So do we have to memorize it as a formula? That's the best answer I can give you. Because it's going to be so frequent, this e to the ax, that if you have to do this every time you need it, and you're going to need it a lot, if you talk about discharging batteries, right, they're going to have this negative e to the negative t behavior, and which is why you are not supposed to charge batteries all the way up to the 100%, right? You should go about like 93, 95 at most and then stop charging. Now, obviously, a lot of people don't pay attention, so they just charged all the way to the top, which is why battery deteriorates. But the thing is that electrical engineers are going to use it. Mechanical engineers are going to have a lot of those, what is called the damped behavior, when you have e to the negative at times cosine blah, blah, blah. There's the term right there. So it's going to be used, right? This stuff is going to be used a lot. Probably it's the best if you memorized it, but now you know where it's come from and you know that you can fix it. So that's so these are the basics of Usub, right? Now we're going to do a lot more problems than this. We haven't even covered half yet. I just want to talk about one more problem, and then we have to move to use substitution with the limits, right? When you have the a and b in a definite integrals. But let's first solve this problem. Can anyone explain how's the tangent x dx a Usub problem?
Because it's essentially two functions using the quotient identity of tangent.
Which would be what?
Sine over cosine.
There you go. That's the boss move. So when you rewrite it as sine over cosine x, which is a quotient identity, very good, you are getting your Usub situation. Now, there are some subtleties here when you have denominators. Your u should always be in a denominator. Not always, but most of the time. Because remember, the du part has to end up in a numerator. So if you are taking, it's not 100% every case. I can make up a case right now where that's opposite, but most of the time. So in this case, right, u is cosine x, and du is sine x dx. Look, I have sine, negative sign, oops, negative sign. So we have to fix that. So I have negative sine x dx, and we can easily now fix this as negative integral of 1 over u du. And what's the integral of this?
Natural log u
Beautiful.
plus c.
Absolute u plus c, yes. Absolute value has to be there. So negative ln of absolute u plus c, and then we plug back our cosine in there. And we now want to do more of this work because we have the those trig pairs we talked about twice already during derivatives of trig functions, and then later on in 4.9 when I talked about it again. See, tangent is not paired with cosine. Tangent is paired with secant. And when you do that, you realize, oh, I have this negative 1 in front. So I can push that inside, which would make this ln of 1 over cosine x, which is another basic identity, which gives us ln of secant x plus c. Now, can this be written as the formula to memorize? Sure, it can. But it's not a basic integral, which is why it was not on the list of our basic integrals in 4.9. And if you go to 4.9, you will see me put the note that go to 5.5, right? But the idea is that you guys now know how to take the integral of a tangent. And cotangent would be the same way, except it's cosine over sine, and you would have and you wouldn't have the issue of the negative, but the negative would come from integration and so on. So those are all the skills, right? They're like a basic skills. And we'll try to take a look at we'll take a look at some of the spicier cases a little bit later. I do want to talk about the integrals that have the limits. But before I go there, looking at all of the stuff we covered so far, what are your questions? Any ideas, fears, anything literally to talk about? Any questions? Well, I guess the Usub is going really well, which is excellent because that's exactly what you need to know all of it for Calc 2. Now, let's go and talk about these integrals, which are called definite integrals, which are the ones that have the limits, the a and b, right? So U sub for definite integrals. Oh, I forgot to talk about back substitution. I can do it later. So what do we have here? Well, we still have the integral that is going to be solved by Usub, but now you have the limits, right? So you have something like this, 1 to 6, right? And you have, let's go with x, and over here go with 3x squared plus 4 raised to the third power dx. So it is a Usub problem. It is not impossible to, foil this, because it's just a cubic, and then distribute x and use basically 4.9 and basic definite integrals to solve this. It's not impossible, but yeah, we can also do the Usub. And now we know the Usub is gonna say put the mess as u, and then do du as 6x dx. And then you say, I don't have a 6, so let me fix that. There we go. And then you have your 1 over 6 integral. And in here you have u cubed du. Like, that's really nice. Like, you took all of this mess, right, and condensed it into something as simple as this. Well, the only issue and a problem now is that you have these limits, and those limits need to be addressed. Now, it's very easy to actually address those limits if you realize that this limit is x1 and this limit is x2. Now, you would say maybe, well, why? How? Well, aren't those a and b on your, right, when you have a function and you're looking for the area under the curve, your a and b are your a and b over here? Well, those are 2x values. And now, when I'm shifting to the u domain, it becomes u1 and u2. Because when you are in x domain, it has to be x, x, x. When you are in a u domain, it better be u, u, u. You can't have mixtures of them. So you can't transform your integral to u domain and leave your limits to be in x domain. That's not possible. You can't decouple things like that. So to change my limits, guys, all I need to do is to use the substitution formula. See, u1 is going to be 3 times 1 squared plus 4. That formula changes with every problem. But the concept of switching from x domain to u domain is the formula that connects those two dimensions, those two domains. So I'm going to stick these numbers 1 and 6 one at a time in the u substitution formula to come up with u limits. And that's 7 on the bottom, right? Because when you plug in 1, which was on the bottom, you plug in 1, 3 times 1 plus 4 is 7. Now the u2, which is the top one, is 3 times, who picked these numbers? Plus 4, that's 36 times 3 plus 4, 90, 108, 112. Terrible, but such is life. So we use u equals 3x squared plus 4 formula to get new u limits of integration. So now, as you can see, my problem turned into a joke, apart from having 112 up there, but that's the job for the calculator. So easy to integrate, u to the 4 over 4, computed from 7 to 112, 1 over 6. Oh, put the 6 times 4 is 24, kick that outside, and then you have your 112 to the 4th minus 7 to the 4th is equal to whatever calculator gives you at the end. So when you have a definite integral, your job is to also convert the limits. Now, some students said, well, how about if I just go back into x variable and then use x limits? Yeah, that's fine. Sure, why not? You can do that. But it's dangerous. And it's dangerous because for that step that you are skipping, you usually don't write the limits because those are the wrong limits for that step. Right? So most of the students will not write limits in this step because they know they'll go back to x and then use the x limits. But by the time they're done with the problem, they forgot that it was a definite integral and then they never compute. They put plus c and move on, and the problem is obviously wrong in that case. Also, there is that extra step of writing an extra step going back to x. I would say that arithmetic calculation is easier than going through extra steps in going back to x value because you'll have to compute it anyway. So why don't you just cut out extra step or two and don't go back to x? So now we have these two worlds, the world of indefinite integrals, which are the plus c ones. You have to go back to x and then put plus c and you're done. But in the world of these definite integrals, by switching the variable to u, I mean switching the limits to u, you don't have to go back to x domain. You can just compute everything in a u domain and move on to the next problem. So it's kind of, it saves time. It saves time. Let's take a look at another Usub problem. It goes something like this. ln3 to ln7 of e to the x divided by e to the x plus 4 dx. So now we need to decipher first what's u, compute du. We need to change our limits, and then the problem will be done. Now let's do this problem together. What do you think we're going to have as u?
The denominator.
Beautiful. E to the x plus 4. Because the derivative of this whole thing will be just e to the x dx, which is on top, and I need those two to be on top because they are multiplied in the substitution. Great. I get to write now that this is equal to 1 over u du. Well, I need to fix my limits. So what is my u1 limit?
Seven plus 4. So they're 11.
Good. So we're
Sorry,
going to
I don't know
have...
why I froze there.
No, that's perfect. So we have we do the bottom limit, right? It's 1 is on the bottom.
Right, sorry.
So ln and e will cancel. You get 3 plus 4 is 7. So the bottom one is 7. How about the top one? E to the ln 7 plus 4. That's 7 plus 4, which is 11. And I'm done. I'm not going back to x domain anymore. I don't have to because everything is now u. So we have ln of u computed from 7 to 11, which is ln 11 minus ln 7. And here comes the ultimate flex, ln of 11 over 7. That's the exact answer. Right? If you want the decimals, you would have to go and deal with that in the calculator. But this is, this is good enough. So this is what we have in terms of changing the limits. Let's do a trig one because I know how much you love and respect trig. So let's go and say you have tangent squared x secant squared x dx from let's not use negative. Let's just say pi over 6 to pi over 4. And let's see what you get. Remember what I need. Function derivative pair. And I also need new limits, u1 and u2. Any ideas?
Would u be secant x?
That is a very good guess. Secant x, and then the du, derivative of secant, is secant x tangent x dx. Now, when you do the substitution, you see how you have two secants, but there is only one tangent, right? So you would peel off one secant, and then you would still have one tangent floating around. And that's a problem. So we need to reverse this. By the way, these are some of the hardest problems of Calc 2 with the secant tangent pair when you do the trigonometric integrals, which are mainly done by U substitution, which is why we are dealing with it here. It's actually reversed. Derivative of tangent is secant squared, and that helps us a lot. So derivative of tangent x is secant squared x dx, and then you can just have u squared because it's tangent, and if you square both you get u squared. So you have your u squared du. So tangent squared is u squared, and secant squared x dx is du. And that takes care of the substitution part. Now we still need to deal with the limits. So how much is tangent of pi over? How much is a tangent of pi over 6 for the lower limit? So the lower limit is going to be tangent of pi over 6, which is root 3 over 3. And the upper limit is tangent of pi over 4, which is simply 1. No more trig, guys. This is just u cubed over 3 from root 3 over 3 to 1. So 1/3 root 3 over 3 cubed minus 1 cubed, and that's going to give you some number. What do we have here? We have 3 root 3 over 3 times 3 times 3 minus 1. The reason why I'm writing it this way because I want to cancel. So I have 1/3 and then root 3 over 9 minus 1. Like, that's the exact answer. You can go get the decimal if, you know, that makes you happy on Saturdays. But this is technically it. I am not going anywhere else. So we transformed this terrible integral, right, into technically x squared, guys, right? And then we switched the limits so that we can easily compute the values, right? And we don't have to go back. Now imagine, right, here you're plugging back tangent so that you can put your pi's in the limits, right? It makes it worse. So this polynomial calculation was straightforward. So convert your limits. It will also save you the headache of forgetting that you had limits and, right, not working on it. So, you know, it's much safer, much better if you convert the limits. All right, 2 things left and we can retire this section. Obviously you guys will hopefully watch the older ones as well from my previous years, and or Khan Academy is like so many of these places where you can find Usub, tens of thousands of videos on YouTube.
Hey, Professor.
Yes.
I have a quick question. So just regarding that last problem, would it be possible to get the same answer if we were to, I guess, try to simplify the original function? So let's say I changed each identity of tangent squared and then secant squared x, and then ended up with sine x squared. Sine squared x over cosine squared x times 1 over cosine squared x, and then combine them and then go from.
Unfortunately, no, because you have way too many sines and cosines and you don't want to have them even. You
Okay.
are going to learn those techniques in Calc 2 in a trig section called trigonometric integration. I believe it's like 7.3. But that is literally opening the gates of hell. Like, we are trying here to stick with the basic integration pairing without using the formulas which you will have to use in Calc 2, which is why I'm going to have a special Calc 2 prep section where I'm going to specify all the sections from Calc 1 and all of the trig formulas you need. But anytime you have the sine and cosine raised to the even power, you are opening the doors for this demon to be summoned, to put it mildly, which immediately introduces a lot more issues down the line. Now, this cannot be avoided in certain problems in Calc 2 that you will see, but right now we're going to keep it right at the basic substitution. As you can see, I used sines and cosines everywhere. We did not have anything of the heavier. Now, the fact that you know that these things can be transformed are amazing, because that will make your calculus 2 walk in a park, literally. If you see the identities, if you see the other approaches to the problem, great. I'm also going to point out that there is something like this that in some cases will have to be used, right? Oop, that's a secant. Oops. Right? The Pythagorean identity for the same pairing, which will be used a lot as well in Calc 2. But that's, again, that's the Calc 2. I am very careful what integrals I put in the Usub for Calc 1, because some of these will be repeated in your Calc 2 course, like the Calc 2 and your trigonometric integrals, right? So you see secant tangent pair, and I'm telling you what are the formulas that you will be using, which is all Calc 1 and pre-calc, and here we go, right? So when we jump into this is a problem that Calc 1 is still using. You see my Usub over here. From this step, I hope you guys see that it's a Usub step, but the pairing over here was a little bit harder to see. And pretty much each one of these, this is actually also Usub that we didn't write down, but going from cosine AX into sine AX over A, that's a Usub part we didn't write. Over here, here's your Usub, you can see it. Here's a Usub over here, you can see it. Like literally every problem. And this is why I say you don't know Usub, you're done, unless you learn that along with your Calc 2. So you just have to know some of these things going in. And I am just picking those very basic problems. So your problems, guys, will look like this. Integral of tangent x dx, integral of cotangent x dx for those basic identities. Integral of cosine nx with the given single sign, or integral of sine raised to some power given single cosine. And then integral of tangent raised to some power given secant squared x dx, because that's a basic substitution. Like these are the Calc 1 variations of problems where this n can be literally any power. Could be a square root, could be, right, 30. It doesn't matter because it will end up being u to that n. So it doesn't matter whether it's a square root or a cube root or a 30th, right? It's not a problem. But this is your Calc 1 realm. When you go to Calc 2, then you get an m power there. And that's going to create Calc 2 substitutions and headaches that you are dealing with when you are in Calc 2. But knowing the first step from Calc 1, basic substitutions, helps a lot when you go into Calc 2 trig integrals. And you've probably seen, right, that right after trig integration, the next lecture is called trigonometric substitution, which, right, see trig sub underneath? Says 8-3 trig integrals, and the next one is trig sub. Now the trig sub is not a U sub, it's trig sub. So in this case, you are going from the problems that look what you would say normal into problems that look abnormal, which are just trig problems, right? So these are the things, right, that you will have to deal when you are in Calc 2, which is why I have to have these honest talks to you about knowing Usub, knowing trig going into Calc 2, because I don't want you to get slain over there or discouraged, right? It's not impossible. Calc 2 is a very easy course if you are prepared. But if you weasel your way out from Calc 1 by having Czech solve your problems, yeah, Calc 2 is not going to be pretty because your knowledge is zero. Right? So you have to be very careful with these ideas and these things. The next problem is also trig, and I want to solve that problem using U substitution in two different ways. It's probably one of my favorite problems it became favorite problem. It's a very simple sine 2x dx. And immediately we can use the I know, right, situation where you say, oh, integral of sine x dx is negative cosine x plus c, plus c. And you immediately know that your u is supposed to be 2x and your du is 2 dx, and you have to fix that. and you are done. So sine u du, and you can just do the cosine here, and you're done. So negative cosine u plus c, that's negative 1/2 of cosine 2x plus c. And maybe you memorized this one as well as a formula from 4.9, where we said that the integral of sine or cosine, whatever, of ax dx had that situation divided by a, just like e had it. I mean, eventually you'll learn that hyperbolic functions, trigonometric functions, and exponential functions all belong in the same group. They're all the same thing. But that's eventually, not now. Which is why the rules for integrals and derivatives are the same, and you always have divided by that a that it's hanging in front of x. So this is the most basic approach to the problem, where you immediately see your u substitution, and you say, well, that's easy. All I need to do is to just replace this 2x with a single u, and the problem is done. And that's the way that I will do it every time. But we can also flex, right? Sometimes in life you just want to flex. And here we go. Right? You use the identity. So when you use your trig identity, sine 2x is 2 sine x cosine x, and then I kick 2 outside because it's a constant. And now we see function derivative pair. U equals sine x, du equals cosine x dx. Derivative of sine is cosine. And I look at that. It's just beautifully, right, laid out right there for us to just say, oh, well, that's u du. Right? We vacated trig completely from picture by using the identity. So the previous way, it's the same problem, same technique, but the different approach within that technique. That's very rare in mathematics. And it's just because this trig is so awesome. That's why we can do it. So you can see that I did not vacate trig from my substitution, with the substitution I made. Trig is still there, and the whole problem was trig. But look at now, right? No trig. And this is 2 times u squared over 2 plus c. These guys cancel, and you just have u squared plus c. Well, that's sine squared x plus c. Right? That's it. There's nothing else there. Now you might say, well, wait, hold on. How's that the same as the answer up there? Because it doesn't look the same. Well, they are the same when you know the power reducing formula from calc. It was the one that I wrote earlier. The sine squared x is equal to 1 minus cosine 2x over 2. Like, you can see your negative cosine 2x right there in front of your eyes in that formula. So if I use this formula, right, which is that, I will just have this to be equal to 1 minus cosine 2x over 2 plus c. Break this into 2. And then let c absorb 1/2, which is the move that in Calc 2 is still, you're not comfortable with it, but constants can be absorbed. These constant terms, like 1/2 there, can be absorbed by that c into just a c. And there you have it. It's the same answer. So this problem is kind of a very interesting problem. just because we can solve the same problem using the same technique in two different ways because of the trig identity. All right, in the last 10 minutes of the lecture, we have something that is called back substitution, and we are done. Now, this is rare. It does pop up here and there, but it's rare. Back sub. Integral of x square root of x minus 1 dx. If I ask you for function derivative pair, you can't find one. It doesn't exist in this problem. Because your three functions, right, that you have, which is x, x minus 1, and square root of x, right, none of them has the derivative, right, on that list. All of our previous lists had it. But these are some anomalous cases that, could be solved by a little bit of, I guess, voodoo on the side. If you go and say u equals x minus 1 and du equals dx because the derivative of x is 1 and, right, you move dx to the other side, you would be able to replace everything except the x in front. So you still have this x, and then you have a square root of u and then du. And that's an issue. But there is a very simple fix, because from this substitution equation, you know that x is equal to u plus 1. So u plus 1. Now, that is, a good mathematical flex right there. And not too many problems will have that flex. So maybe you see it twice in your entire Calc 2, maybe once or twice in Calc 3. Like it's very rare. But the trick is that when it comes up, most of the students are, huh? Because you vacate this out of your brain immediately when I say it's very rare. It does pop up here and there. And now we have a simple u to 3 halves plus u to 1 half when you distribute. And these become basic integrals that you solve using your section. So 2/5 x minus 1 to the 5 halves plus 2/3 x minus 1 to the 3 halves plus c. The solution looks terrible, but I am going to encourage you to take the derivative and get back your x root x minus 1. But, it's a method. And sometimes when you are short of substituting one value here and there, back substitution, which is this orange, right, part, is what is new. So technically this over here is your back substitution. All right, so now let's just take a look at the end of this. Take a quick look at the formula, which I promised and that you will never use because you've seen the procedure, you've seen the way you think, and now you're going to see when I write the formula that's completely useless. You learned that the derivative of the function composition is the derivative of the function with a g plugged in times the g prime of x. Which means that if you integrate f prime of g of x times g prime of x dx is going to be equal to f of g of x plus c. Now, let u be g of x, which will immediately make that du is equal to g prime of x dx, which you can see in here. And that creates that integral of f of u, f prime of u du is just equal to f of u plus c. It's, it's not something that you really get to use in this form. It is function composition, like that's, it's a Usub problem when you see function composition, because literally, not every, but almost every problem, right? This is function composition. X minus 1 is inside the square root. Over here, 2x is inside sine. That's a function composition. Going up here, it's not a function composition. Actually, it is. Tangent is inside x squared. Right? X squared is the outside, and the tangent x is inside, and then you stick this one in, and you get tangent squared. So it is a function composition, actually. This one is function composition where ex plus 4 is inside 1 over x function. So it is a function composition there as well. I mean, every one of them has to be, because clearly, right, this is inside a cubic function, and so on. So it is function composition. And it is backwards chain rule, so you're expecting function composition to be the core of the thing. But it's just so hard to look at the formula and make sense of anything. This formula doesn't correlate very well, right, to what you have in a problem. So we learned the procedure. We learned a way to think about function derivative pair, about, okay, I hit the brick wall. It doesn't work this way. Okay, turn around, run the other way. Right? It's more of a procedure and your experience in doing this rather than you trying to find some kind of formula, because the formula will never, ever help with Usub. It's only experience, and I really hope you guys go and do like 100 problems because your Calc 2 depends on it. Any questions, concerns, anything? Because this is the end of Usub. Nothing? All right, bye.